All right, this is section 5.2. We're talking about power functions and polynomial functions. So power functions, it's a function that can be represented in the form f of x is equal to k, x, and then raised to p. So the k, or the number in front of it, and p, the number that x is raised to, those are going to be real numbers. And k is also known as the coefficient. So the coefficient of, say, this right here would be 5, the number right in front of x. Okay, so let's look at this one. Is f of x equal to 2 raised to x a power function? Well, no, because what it's raised to is a variable and not a number. Like over here it says p has to be a real number, and that's what x is raised to. And the second thing is a variable is not raised to a number is raised to a variable. So this right here is actually what we call an exponential function, which we'll get to in chapter 6. Okay, so here's some examples of a power function. So for this first one, a constant function, you could write this as 1 and x raised to 0, because x, or anything raised to 0, is just 1. Okay, so this would really be 1 times 1, which would give you just 1 again. Okay, so that's why a constant function can also be considered a power function. Okay, this one is raised to 1, and then you got 2, 3. Now this one you could write as x raised to negative 1. This would be x raised to negative 2. This would be x raised to 1/2. And this would be x raised to 1/3. So all of those are power functions. Now let's go to polynomial functions. So we're going to let n be a non-negative integer. A polynomial function is a function that can be written in this form right here. Now that's just a really general way of writing, say, 2x raised to the 4th plus 5x raised to the 3rd minus 3x raised to minus 4x plus 19. Okay, notice how it's in this form right here, and it starts with a larger number. So we started with a 4, 3, 2 that's raised to 1, and you could write this as x raised to 0 because we know that x raised to 0 is just 1. So it goes in descending order. Okay, this is called the general form of a polynomial function. And each number right in front of your variable, those are what we call coefficients. So the 2, the 5, the negative 3, the negative 4, and the 19, that's what we would call a coefficient. And those can be any real number. But a sub n, the very first one, that can't be 0. Okay. So each expression, so each entire expression, let me get rid of some of this. So this first one here, or this whole thing here, that is called a term of the polynomial. So I have 1, 2, 3, 4, 5 terms in this polynomial. Okay, and there's just some examples of a polynomial function. It doesn't always have to be written in the general form. It can be written something like this right here. Okay, so what we're going to do is we're going to kind of break apart the polynomial into two things. We got a degree and a leading coefficient of the polynomial function. Okay, so when we have it in, the powers are going in descending order. So you start with the biggest and you go down to the smallest. So when we have it in descending order, then the very first number right in front of your variable, so this right here, this is your leading coefficient, and then x raised to whatever number, whatever that number is, that is the degree of the polynomial. And the entire thing, when you put the leading coefficient and the x raised to whatever number, that is called the leading term. Okay, so let's look at this right here. Find the degree and the leading coefficient of the polynomial. Also determine the maximum number of real zeros. Okay, first I'm going to put it in general form. So negative 4x cubed plus 2x squared plus 3. So it's going in descending form. So this right here is my leading term. This negative 4 is my leading coefficient, and the degree of the polynomial is 3. So leading coefficient is negative 4, degree is 3. And it says also determine the maximum numbers of real zeros. Well, it's whatever the degree is. So the max number of real zeros, that would be 3. Okay, so same thing. So I'm going to check to make sure it's in descending form, which looks like it is 5, 3, and then raised to 1. Okay, so our leading coefficient is 5, and the degree of, so from this right here, that's 5. The degree of this polynomial is also 5 because it is raised to 5. And the maximum numbers of real zeros, well, that would be the same as the degree, so there should be 5 real zeros. Okay, so the leading coefficient, number 1, it's not in descending order, so negative x cubed plus 6x minus 2. So the leading coefficient is, if there's nothing in front of it, there's assumed to be 1, so it's negative 1. The degree is 3, and the maximum number of zeros is also 3, the same as the degree. Okay, so this one, we could write it as, since it's just a number, 3x raised to 0. So the leading coefficient is 3. The degree is 0. And also the maximum number of real zeros, well, that will also be 0, the same as the degree. Okay, now let's talk about end behaviors of power functions. So if you've got an even power and you have a positive constant, so if you have those two, then as x goes to negative infinity, like here, this is negative infinity for x, your y function, so your y function right here, that's going to go towards positive infinity. I'm reading this right here. It's going towards positive infinity. So this is positive infinity for y. This is negative infinity for y. This is negative infinity for x, and this is positive infinity for x. Okay, so as x goes to positive infinity, well then what's your graph doing? It's going to positive infinity as well. So if you have those two, an even power, so say an even power, so 4, and a positive constant, so say 5, so you have something like that, then the ends of your function will both be going straight up to positive infinity for f of x. Now, if you've got an odd power and a positive constant, so say x raised to 5, and say this is, we can say it's 5 again, it's still positive. Well, in that case, as x goes to negative infinity, so I'm reading this right here, your function will go down to negative infinity for f of x. When you go to positive infinity for x, then your function will go to positive infinity for f of x. Now, if you've got an even power and a negative constant, so say negative 4x raised to 2, then as x goes to negative infinity, your function will go to negative infinity. As x goes to positive infinity, your function will go to negative infinity. If you got an odd power and a negative constant, so negative 3x raised to 7, as x goes to negative infinity, your function will go to positive infinity. As x goes to positive infinity, your function will go down to negative infinity. Okay, now all of this information I just gave you for power functions, that is also the same for polynomial functions. We just need to look at the leading term of a polynomial function to see what the end behavior would be. So let's look at this right here. So we have a polynomial function, 6x raised to 5 minus 4x squared plus 9x7 plus 13x raised to 18 minus 2x raised to 4. Now the leading term of this one, remember that would have the x value raised to the highest number. So that would be this right here. And let me get that positive in there as well. So that's my leading term. So notice I have an even power 18, and I have a positive leading term. So come back over here. Okay, so an even power and a positive constant or leading term. So should both go up as x goes to negative and positive infinity, our f of x should go to positive infinity. So as x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, our function will also go to positive infinity. So on our graph, this function right here, if we plot it, we know that the ends will be going up somehow. Now here's a graph of that function that we just looked at, and notice how as x goes to negative infinity over here, the function goes up towards positive infinity for y, or f of x. As you go to positive infinity for x, your function is again going straight up to positive infinity for our f of x, or for our y values. Okay, so let's look at this one, and we'll determine the end behavior. So it looks like the leading term for this one is now negative 13, x raised to 18, and our degree is even, but now our leading coefficient is negative. Okay, so still even power, but now we have a negative coefficient. So both the ends should be going down towards negative infinity for f of x. So as x goes to negative infinity, our f of x will go to negative infinity. As x goes to infinity, f of x will go to negative infinity. Okay, here's a graph of that function. Notice how both of the, as you go to x goes to negative infinity and x goes to positive infinity, your f of x is going down towards negative infinity for f of x. Okay, so for this one, here's our leading term. Notice that now we have an odd number here, or odd power, and a negative coefficient. So an odd power and a negative coefficient. So as x goes to negative infinity, we should be going upwards to positive infinity for f of x. And as x goes to positive infinity, our f of x should be going to negative infinity. So it's the opposite of each other. Okay, so as x goes to negative infinity, we should be going to positive infinity for f of x. As x goes to positive infinity, negative f of x should be going to negative infinity. Now this chart right here, I don't have a simple way to remember it, so you just have to remember the 4 cases here. There's not a simple way to remember it that I know of anyway. Otherwise, I would share it with you. Okay, so let's look at the graph of this one as well. Okay, notice as x goes to negative infinity, our function is going upwards to positive infinity. As x goes to positive infinity, then our function goes down towards negative infinity. And last one here, here is our leading term. So we have a positive number, but an odd power. Okay, so odd power, positive number. As x goes to negative infinity, our function should go to negative infinity. As x goes to positive infinity, our function should also go to positive infinity. So as x goes to negative infinity, our function goes to negative infinity. As x goes to positive infinity, our function should go to positive infinity. And let's take a look at that graph as well. Okay, notice here, as x goes to negative infinity, our function is going downward to negative infinity. As x goes to positive infinity, our function goes upwards towards positive infinity. Okay, consider this polynomial function graph below. Determine if the graph goes to positive infinity, negative infinity, or 0. So as x goes to negative infinity, going this direction, our function is going upwards to positive infinity. As x goes to positive infinity this direction, our function is again going up to positive infinity. Okay, as x goes to negative infinity, our function goes up to positive infinity. As x goes to positive infinity, our function goes down to negative infinity.